My friends, this is a tricky limiting reactant and excess reactant percent yield problem with weird units with density and gases. And this question here is part of a compilation of various questions that I put together on limiting and excess reactants. So if you want, you can check out all the other ones or the longer series or this tricky question just right here, right now. If 5.40 milliliters of bromine, now we have a volume and a density, that's it, reacted with 150.0 mils of C2H2. So this would be ethine. It's a gas right here. 25 degrees Celsius under a pressure of 1.1 bar, that's the pressure, to produce a percent yield of 85%. What was the actual yield? Now, we know this is a limiting reactant problem because we have a balanced equation. And always check, make sure your prof has it balanced. Sometimes they try and throw you for a loop and not balance their equations, and you have to do it without telling you. But this is balanced. And we have information. We have initial conditions for each reactant. So if we do that, one of these are going to be in excess, and one of them is going to limit how much of this we can make. So we're going to look at each reactant separately. We'll start off with the bromine, and we're going to look at if all of these 5.40 milliliters reacted fully, how much of this product, this tetrabromoethane is what it is, but can we make? So we're going to do stoichiometry to go from amount of bromine, volume of bromine, to grams of this product here. This is stoichiometry, 3 steps. You can check out my 3-step process if you're confused. But I'm going to go through this relatively quick. So we want to get to grams of this product here. So we're going to start off with 5.40 times 10 to the negative 3 liters. That's just converting this to liters here. Now we want to get to moles first because we need to use the mole bridge to find out how many moles of this product there are. So we can't go from liters to moles right away. We have to cancel out with this density. Oh, this density is in mils. So actually, let's make this milliliters here so that we can cancel out the milliliters. And this is of bromine, Br2, Br2, and we want to cancel out milliliters of Br2. We want grams of Br2, and bromine weighs 3.12 grams for every 1 milliliter. So now that we're in grams of our one reactant, we can go straight to moles using the molar mass like we've always done. We want grams of Br2 to cancel out, and we want moles of Br2. For every 1 mole of Br2, we can look on the periodic table. Molar mass of bromine times 2 is 159.809 grams. So our grams of Br2 cancel out. Now that we have moles of bromine, we can use the mole bridge to find out the moles of this product here. And so we'll do that. So we will, for every, maybe I'll make it a little bit smaller, just to save space. So I have enough space. We want moles of Br2 to cancel out. And we want moles of this product. Moles of, I'm just going to call this P for product, if that's okay, just to save space. And for every 2 moles of Br2 of bromine that react, we make 1 mole of product. So there's 1 mole of product for every 2 moles of Br2. Moles of Br2 will cancel out. So we will get 1 point, that'll give us moles of product, but we want grams of product, right? So let's go to grams here. And we want moles of product to cancel, and we want grams of product. Now the molar mass of this, you can look in the periodic table, 2 times the molar mass of carbon plus 2 times the molar mass of hydrogen plus 4 times the molar mass of bromine works out to be 300. So for every 1 mole of the product, we get, it weighs 345.7 grams. Okay, now we'll plug that into our calculator. So 5.0 times 3.10 grams divided by 159.809 grams divided by 2 times 345.7 and 18. Does that make sense? 18.22 grams. 18.22 grams of our product, which is C2H2Br4. And 3 sig figs, so we have 3 sig figs here. So this is how much we would produce if the bromine reacted completely. But we need to look at the other reactant, the C2H2, to see how much product we would produce if it reacted completely. So we're going to look at the other one, C2H2, and we need to know how many moles of this there are. Well, we don't have a volume or a mass. We have a gas, and we have a volume, a temperature, and a bar. So we have these gas conditions. So in order to find out the number of moles based on gas conditions for a gas, we need to use the ideal gas equation, or the perfect gas law here. PV equals nRT. It doesn't say so, but we're going to assume it's an ideal gas or a perfect gas. N is the number of moles, so N equals PV over RT. Now we just have to make sure that our units work. P is our pressure, so pressure is 1.1 bar. 1.1 bar. And our volume is 150 mils. I'm just going to put this into liters, so move the decimal over 3, 0.1500 in order to divide it by 1,000. Now, R is our gas constant. I'll do the R last because our units have to be in moles. So the temperature is 25 degrees Celsius. Now, we got to put that in Kelvin. So 25 degrees Celsius in Kelvin, we got to add 273.15 to get Kelvin, so that's 298.15 Kelvin. So the R we use has to cancel out bars, liters, Kelvin, and moles here. So we will use the one that is 8.314 liter bar per mole Kelvin. And it's always good to cancel the units. Bars cancel, these liters cancel, Kelvin cancels. So we have 1 over moles down here. So we could kiss and flip, and then we get moles for the units here. Same thing up here. I don't think I canceled my units, but moles of P cancel out moles of product, and we're left with grams of product. Okay, so let's plug this into our calculator. 1.1 times 0.150000 divided by 8.3145 times 298.15 is really small number. Okay, well, it is a gas. 6.656. 6.656. 6. Oh, I'll make it blue. 6.656 times 10 to the negative. Was it 5 moles? I better double check this. Okay, 5 moles, and this is of our product, C2H2. Okay, now that we know how many moles of our, not products, or reactant of our reactant there are, we could find out how many moles of our product there are. And it's a 1-to-1 molar ratio. And I'll just write it out just so everything is complete. And your prof likes to see that as well, likes to see all the steps. Even if it takes 30 seconds or so, it's worth it. And it could save you in case you did a silly error. I sometimes do them. So we have moles of C2H2 that cancel out with here, and we want moles of our product. I'll just call it P. And it's a 1-to-1 molar ratio. And in this way, our units cancel, so we feel pretty good about ourselves. Oh, now that we have moles of our product, we don't want moles, we want mass, right? So we want to cancel out moles. Moles of product, we want grams of our product. For every 1 mole, the product weighs, what is it? 345.7 grams. 345.7 grams. Okay, we plug that into our calculator. So, oh, I just deleted the number. Oh well. 656. I could have put this in scientific notation. 1, 2, 3, 4, 5. Okay, I think that's good. 656 times 1 times divided by 1 times 345.7. 0.02301. 0.02301 grams of C2H2Br4. Okay, so we have this many grams, assuming that the gas reacted fully. But if the other one, bromine, reacted fully, we could make 18 18 grams, holy. So we have enough bromine to make about a little more than 18 grams of product. 18 grams, we have enough bromine to make almost 18 grams of product, but we only have enough of the gas of the C2H2 to make like a fraction of a gram. This is like 23 milligrams of product. So we can't make this much product because we don't have enough of the gas, the C2H2. So this is limiting how much we can make. So our theoretical yield, I'm sorry if it's messy, equals 0.0230 sig figs, 1 grams. How many sig figs do we have? Oh, we have 2 sig figs here only. So this one doesn't matter. Yeah, we only have 2 sig figs. So 0.023 grams of C2H2Br4. Okay, so that's our theoretical yield. We want to know what the actual yield is based on the percent yield. So from that, we use our yield equation. Percent yield equals the actual yield, AY actual yield divided by the theoretical yield. I remember this as alphabetical order, A over T times 100%. Well, we want to know what the actual yield is. So the actual yield is going to equal the percent yield times the theoretical yield, all divided by 100%. And so what's percent yield? I think it was 85%. Is that right? Let's see here. 85%. That's right. 85%. Theoretical yield is right here. Oh, we'll keep this extra digit. Oh, it's a 0, but we'll keep one more digit and then we'll round at the end after. 230 grams divided by 100%. Okay, time to partay. We're almost done. Times 0.023 divided by 100, 0.01955. So 0.01955 grams. Because our percent yield is in 2 sig figs, and usually the percent yield is rounded to the nearest whole number. We're stuck to round here. We'll round the 5 up because this is an odd number. So 0.020 grams is our actual yield of C2H2Br4. Right on. Awesome possum. Well, hope you enjoyed it. Hope you got some benefit from it. I really enjoyed it. And after this example and the other examples that I've created for or did videos on limiting and excess reactants and yields and the 3-step stoichiometry method, you should be so good at this stuff. Practice, practice, practice. And I hope you do well in your exams. Thanks so much for watching. I'll see you in the next one. Cheers.